this series of videos, we're going to solve question 3 on problem sheet 5. In question 3, we're asked to solve the following initial boundary value problem for the wave equation. Okay, so we want to solve the wave equation 1 subject to the Dirichlet boundary conditions 2 and 3 with prescribed initial profile f and initial speed g. Okay, so physically this could model something like the transverse oscillations of a string with clamped ends with initial profile f and initial speed g. Okay, so in part A, we're asked to show that we can decouple the wave equation 1 into two ordinary differential equations by seeking a separable solution. So what we're going to do is we're going to seek a solution to the wave equation 1 of the form u of xt is equal to big X of x times big T of t. So what we're going to do is we're going to multiplicatively decompose the solution u into a spatial part x and a temporal part t. Okay, so what we're going to do is we're going to substitute this ansatz for u back into our wave equation 1. Okay, so if we do this, then 1 becomes, well, the left hand side is just the second derivative with respect to t of xt, and that's equal to c squared times the second derivative with respect to x of xt. So on the left hand side, x is a function of x only, so we can pull it outside the partial derivative with respect to t. So the left hand side becomes x times d2 t squared of t. Similarly, we can pull the t outside the x derivative, so the right hand side becomes c squared t times d2x 2 times x. Okay, now here on the left hand side we have a partial derivative with respect to t on a function that depends on t only, so that's the same thing as just the regular derivative. Okay, so we can write the left hand side as x times d2t dt squared. Similarly, on the right hand side we can write the partial derivative with respect to x as just the regular derivative. So the right hand side becomes d2x dx 2. Okay, so what we want to do is we want to write the left hand side as a function of t only and the right hand side as a function of x only. To do that, what we're going to do is we're going to divide both sides of this equation by c squared x times t. Okay, so if we divide both sides by c squared x times t, well, the left hand side is just going to become 1 over c squared t times d2t dt squared, and the right hand side is just going to become 1 over x times d2x dx2. Okay, and of course we can just flip those two terms around, so we can write the equation likewise as 1 over x times d2x dx2 is equal to 1 over c squared t times d2t dt squared. Okay, now here the left hand side is a function of x only. Similarly, the right hand side is a function of t only. And the left hand side has to be equal to the right hand side for all x and t. Now, of course, the only way for that to be true is if both sides are equal to some constant. Now we're just going to call that constant minus lambda, okay? And minus lambda here is a constant. The minus is introduced for convenience. Okay, now here, this equation here is really two separate equations. It's the x part is equal to minus lambda and the t part equal to minus lambda. So let's write those individual equations out separately. Well, the first equation would be 1 over x times d2x dx squared is equal to minus lambda, and the second equation will be 1 over c squared t times d2t dt squared is equal to minus lambda. Okay? of course then we can rewrite these two equations. If we multiply both sides of the first equation by x and bring the term on the right hand side to the left hand side, we can write this equation as d2x dx squared plus lambda x is equal to 0. And similarly, if we multiply both sides of the second equation by c squared t and then bring the term on the right hand side over, we can write the second equation as d2t dt squared plus c squared t lambda is equal to 0. And of course we can write the c squared t lambda likewise as lambda c squared t. Okay, so we've shown here that by seeking a separable solution of the form shown here, we can decouple our partial differential equation 1 into two separate ordinary differential equations. Okay? Now in the most general possible case, lambda, which remember is a constant, lambda is a complex number. Okay? But if lambda is a complex number, then we would have complex solutions for x and t, and hence for u. Now for physically meaningful solutions, we have to take lambda to be real. That means that lambda can take three possible ranges of value. 1, lambda is less than 0, 2, lambda is equal to 0, or 3, lambda is greater than 0. Okay? So in part B, what we're going to do is we're going to solve these two ordinary differential equations for those three possible cases.